All right, so this is going to be a second lecture of energy. Okay. Till now, we completely understand how do we define energy. Okay. Then what are the following forms of energy, kinetic and potential broadly. Then we have seen the transfer and transformation. They are different. Transfer means same kind of energy transfer from one body to another body. That is transfer. Change of position is transfer. Okay. Change of position is transfer. Transfer of energy. When an energy is being transferred from one position to another position or one body to another body, it is transfer. And transformation is different when it changes form. Change in form. This is transformation. We have talked about that enough. Then the last thing we did was conservation of energy.
Yes.
Conservation says the energy remains conserved in an isolated system. There are multiple ways of defining conservation of energy. You can say energy is conserved in an isolated system. Isolated system means you are not disturbing the system. System remains same for the observation as long as you are observing. So from the point of initializing the observation and then finalizing the observation, okay, you are not doing anything to the system, then the system is said to be isolated. For such a system, the energy is conserved. So the whole universe can be considered as an isolated system because we don't know what lies external to the universe. If we don't know there lies anything external to the universe, we think that there is nothing which is disturbing the universe also externally. So universe can be treated as an isolated system, and the energy of the universe is conserved, okay, from the point of Big Bang. Okay, in the systems also we shall know open system and closed system. Systems are of two kinds. Now this is in the conservation of energy only, open system and closed system. So from the name itself it is very clear. A closed system is like a vacuum flask containing a hot soup. Almost no thermal energy escape. Your thermostat, tiffin boxes, your water bottles. Thermostat. Why I'm saying stat? Stat stands for static, constant, not changing. Thermo stands for temperature. Such a material which do not allow the temperature change. If such a system is made by thermostat material, the system is open. The system is closed system because it is not allowing any change. On the contrary, open systems are the one which are very prone to the changes. Okay, like you are having a soup in a bowl which is set idle on the desk, so there will be heat transfer between the air and the soup. The soup will get cold, stall in some time, right? That's an open system. So the conservation of energy ideally applies on the closed system. Conservation of energy applies ideally on the closed system.
Yeah.
Because system is open, so energy will not be conserved. Also, what is the way of understanding conservation of energy? Initial energy equals final energy. That's it. Okay, if you have started your observation at a certain time and then you observe the energy count, the energy count is, let's say, 100 kilocalories, 1000 kilocalories, and at the end of observation you are seeing the energy count remains same. That means the system is isolated. The law of conservation of energy is strongly applied. Okay, your system follows that particular law. Since conservation of energy is a universal law, so it's not in our hand to make it apply or no. It has to apply, it has to be there. It always applies for a closed system ideally. Okay, it's a law. Okay. Now we are starting the new topic from here, which is work.
Work is a topic. Okay.
Work isn't within the energy chapter only. Okay, I told you already in the starting of lecture number 1, energy and work, they are analogous to each other. Mathematically same, conceptually different. They are treated as the same physical quantities in physics. Work and energy are same. The unit of work is also joules, like energy. In fact, the formula of work and energy is also same. The formula of energy was force times distance or displacement. S is the representation of displacement. F is the representation of force. So the formula of energy is force times displacement. If you want to understand that, I have a wooden block. I apply a force of F newtons on the block, and the block moves 2 centimeters or 2 meters, new position of the block. So how much energy you have applied? Just multiply the force you have applied with the distance the block moved. Then you will get the energy required in moving the block. That's it. What was the amount of work? The same thing. Force times displacement. What I'm saying is energy and work, they are mathematically same. Conceptually, they are different, because how do we define energy? Sorry. How do we define energy? So energy was the ability of doing work. And what is work? Work is the way of spending energy. That's it. They are interrelated to each other. Work is a way. When you will work, you will use some energy. There is a concept of zero work. Zero work, which is well explained. If you are there and you are holding a briefcase over your head, okay, you are holding a briefcase over your head and you are moving all the way. Doesn't matter how many kilometers you are moving, but physics says your work is zero. You have done zero work in moving the briefcase. You have moved, you have changed your position, but in moving the briefcase, you have done zero work. What is the physics behind that? So it lies in the vector understanding. I told you physical quantities are of two kinds, vector quantity and scalar quantities. We are not going in that. Always remember, when your force, okay, when you apply this particular formula of work, force times displacement, and I want to make the value of work zero, since I am telling the work here is zero. What should be zero here? Force, either force is zero or displacement is zero. Force is not zero because there is a weight of the briefcase which is acting downward, right? In this formula, you have to take that particular displacement which acts in the direction of force. What I'm saying, in the formula of work done, they're not just any random displacement and any random force. No. If you are choosing a particular force, so the force of the briefcase is the downward weight of the briefcase. That's it. The weight of the briefcase is the force which is acting downward. So in the formula, the S value, the displacement value has to be in the downward direction. So have you moved the briefcase down? No, you are only moving the briefcase forward. There is no downward displacement. There is forward displacement, which you will not count in the formula. If the force is downward, displacement has to be downward. And since there is no downward displacement, the value of displacement is zero. So 0 times force will give you 0 and the work is 0 this time. So not just in this example, okay? When you feel there is some work, but always check the force and the displacement. They both should be there in the same directions. That's it. If they are not in the same directions, okay, then you will not count that particular displacement. Certainly, the briefcase is being moved forward. Briefcase is changing its position as the guy moves forward. But there is no downward displacement. It has to be there in the formula because the force is downward. Right?
Yeah.
Okay. So in that particular part, they may only ask us numericals. When they will give us force, they will give us displacement, they will ask us for the work done. And the unit of work done will be joules.
Yeah.
For example, they can ask us a question. We are pushing a shopping trolley with a horizontal force. Shopping trolley with a horizontal force of 40 newtons. So there is a horizontal force, okay, and the trolley moves a distance of 6 meters. So it is certain if we are applying a horizontal force, the trolley is also moving horizontal. So both are in the same direction. You can put these values in the formula, which is force times displacement will give you what? 40 times 6, 240 joules. This much of work done you have done in pushing the trolley, in moving the trolley by 6 meters by applying a force of 40 newton. That's it. Okay. These can be the kind of numericals they may form. Okay. Now let's understand both together, energy and work. We already know energy is the ability of doing work. And what is work? Work is mathematically the amount of energy being transferred, a way of doing or spending energy.
Yeah.
When work is done on an object, energy is being transferred to the object. If I push you, then I am transferring some energy onto your body. Okay. So work is done on the object, and the moment the work is done on the object, the energy is transferred to it. Without work, there can be no energy transfer. This is why I'm saying work is a way of energy transfer.
It's a way of kinetic energy.
Yeah. When I pushed you, that's a kinetic energy. I did some work and the energy is stored or showed up in the kinetic energy form. When you lift a box at a certain height, let's say 1 meter from the ground, what is happening here? You are doing some work by spending your chemical muscular energy, which is being transferred into gravitational potential energy. Because when you lift something over a certain height, so it stores gravitational potential energy this time. Okay, so energy is being transformed also when it is transferred by the means of doing work. Okay. Then comes the kinetic energy in broad. So kinetic energy is the energy of motion. That's it. Kinetic energy is the energy an object has because of its motion. An object that is moving must have a kinetic energy. The faster a body moves, more kinetic energy it is having. The faster it moves. So higher the velocity, higher will be the kinetic energy, right? That's what I'm saying. From the definition of kinetic energy, the faster the body moves, more kinetic energy it is having. Because kinetic energy is the energy of motion. It's like a weapon. And you have it, you will be moving faster. So if you need to move something faster with higher velocity, the kinetic energy has to be more. That is a relation between them. If you want more velocity, you have to apply more kinetic energy. The body should have more kinetic energy. Okay, if you want to move a heavier object, you will then also require higher kinetic energy, because it will be requiring more energy in moving a heavier object than a lighter object. It is easier to move a lighter object. So lighter object will require lesser energy. Heavier object will require higher energy. So are indirectly proportional. Kinetic energy is directly proportional to velocity. Kinetic energy is directly proportional to mass. That means if velocity increases, kinetic energy increases. If mass increases, kinetic energy increases. Yes or no? What I'm saying is, if you want to move a certain object with a higher speed, higher velocity, they are same velocity and speed. So the body will require kinetic energy more. If you want to move the body slow, that means low velocity, the body will require low kinetic energy. The relation is direct. Low velocity, low kinetic energy, high velocity, high kinetic energy, direct relation. Okay, this is a sign of direct proportionality. Then, yeah, this sign is directly proportional. If I say, if I get more marks, you will also get more marks. So our marks relation is directly proportional. If I'll get less marks, you'll get less marks. That's it.
Yes.
Okay. If a certain object is heavy, it will require higher kinetic energy to move. If a certain object is lighter, it will require lesser kinetic energy. Okay. So from these two, when I combine them, equation number 1 and equation number 2, when you combine them, I will write kinetic energy is directly proportional to mb, because it is directly proportional to m also, mass also, velocity also. In maths, when you remove the proportionality sign, okay, it is introduced by a equal to sign and with a constant on the other side, k, multiplication. So kinetic energy equals k times mb. That's it. Proportionality sign is changed by equal to k. Okay. What is k proportional here? The k proportional value here is half v. Okay. It is known by observation. So when you will put it in the equation, you get the formula of kinetic energy. Half m b square. You only have to remember this formula, even if you don't remember the derivation. Kinetic energy equals half mb square. If you know the mass of the object that you need to move, if you know the velocity of the object with which you want to move the object, then you can find the kinetic energy of the object. For example, okay, I want to move a truck of a certain mass m with the velocity v. So I must apply a kinetic energy of half mb square on the truck. Only then the truck will move with the v velocity. Okay, this is how we can solve numericals. The units of kinetic energy remain same as of the energy joules.
Sorry, what? I don't get that.
The units remain same for kinetic energy. The answer will be coming in joules, capital J.
Yeah.
Okay. Also, there is a relation of square. That means kinetic energy is not just directly related to velocity, but directly related to velocity square, half mb square. See?
What is that? Can you explain?
Yeah, I will explain. What I'm saying is, it is written right in front of b square, not just b. So kinetic energy will increase on velocity increase, but it will heavily increase. It will square time increase. Earlier I was saying, if you double the velocity, your kinetic energy will be doubled. No, the expression is telling us kinetic energy will square time increase. If you double the velocity, that means you are doing the twice of the velocity. Kinetic energy will increase by 4 times, square times. Square of 2 is 4. If you are doing the thrice of velocity, kinetic energy will increase by 9 times. If you are doing the 4 times of velocity, your kinetic energy will increase by 16 times, square of 4. Okay. But it is only proportional to mass. So if I say, if you double the mass, kinetic energy will be doubled. If you triple the mass, kinetic energy will be tripled.
Okay.
This is the relation here. Okay, so they may form some questions. I'll give an example on that. Yeah, so there is a car moving with the velocity of 50 km per hour. I made the velocity now 100 km per hour. By what amount? By what percentage kinetic energy will be increased?
You said it was initially 50, right?
50, and 50 had become 100.
The speed of the car was 50.
Yeah, the speed of the car is 50 km per hour, which is now made to 100 km per hour. What is the new kinetic energy? I'm not asking the value of kinetic energy. You cannot find that until you're not having mass. I'm finding you the relation. What happens? Will it be twice? Will it be 4 times? Will it be thrice?
Oh, twice.
4 times. Because twice happened with the velocity. So square times change will happen with the kinetic energy. Square time change. So I double the velocity from 50 to 100. Kinetic energy will be 4 times. If I triple the velocity from 3 to 9, so my kinetic energy will be 9 times. If I'm doubling it, so kinetic energy is changing 4 times. That's it. And this is the reason.
What's the reason?
Just a minute. Yeah, this is the reason why we are asked to drive in a certain speed limit. Because velocity is not changing linearly. Okay, certainly, what is energy? See, as you are moving your car with a certain velocity, certain speed, let's say 80 kilometer per hour on highways. So, all right, if you made 80 to 100, just a change of plus 20 kilometer per hour, you have increased your speed by 20 kilometer per hour. You may feel that it's fine. My kinetic energy will be increased by some amount. No, there will be a square time change is happening. The change is not linear. It's not that you will increase your speed a bit, kinetic energy will also be increased by a bit. No, kinetic energy will be increased by a bit square, a larger amount. Do you get me? Right?
Okay.
So a larger change is happening. So you may feel a small change, a slight change in velocity will not matter on highways. But if we collapse, okay, if there happens an accident, so it will be of huge consequences because higher kinetic energy was stored in your vehicle. So the moment your vehicle will be collapsed with another vehicle, that particular energy will be released at a certain time. So you always want your kinetic energy to be reduced somehow. Lesser the kinetic energy, lesser energy will be released at the time of accident. This was one thing, to still within the speed limits when we are driving our car. Second thing is about mass. In earlier days, people used to think heavier your car, safer is your car. More bulky is your car, it will be safer. People used to think like that. Like bulky stands for like more thicker walls, they will protect you. Okay, it makes sense also, it's logical. If you don't know physics, you will agree. Like heavier the car, it will help us to have a lesser consequences of accidents. But right now the physics has evolved. Okay, in the 90s only, German cars were made lighter because they know the principle of kinetic energy. They know the kinetic energy is directly proportional to the mass. So if your car will be lighter, of a smaller mass, the kinetic energy stored will also be lighter.
Oh, right.
And at the time your car will collapse. Okay, so that small amount of kinetic energy will be released.
Okay.
If it is of greater mass, then it will be releasing a huge amount of kinetic energy.
Okay.
That is the case here. So we know both the things now, v square and m, and both have their like applications.
Okay.
This was all about the kinetic energy. So in the question they may form, they will give us the velocity, they will give us the mass, and we'll ask the kinetic energy. You know the formula, half mv square, we'll put the values in the formula, we'll get the kinetic energy value. Or they may give us kinetic energy, they may give us mass, and they will ask us the velocity, v value. So 3 other quantities, 2 will be known, any one will be unknown that they will ask us. Using the formula we can find it. Clear?
Yeah.
Okay. Your answer will only come in joules when your mass is in kgs and your velocity is in meter per second. Okay.
Sure. What?
I'm saying your answer will only come in joules when your mass was in kgs and your velocity was in meter per second. Otherwise, you will not get your answer in joules. It will be in some other quantity. So it is better to change the mass into kgs if it is not given in kgs. To change your speed into meter per second square if it is in some other units. If it is kilometer per hour, you have to change that into meter per second. You know how to do it? Changing from kilometer per hour to meter per second.
Yeah. Yeah.
Okay, then, good. Now the next thing is gravitational potential energy.
What is that?
A kind of potential energy.
Okay.
Gravitational potential energy. So it is that energy an object has because of its height above a reference point. Usually the earth is considered the reference point. So this is my earth. This is my reference point here, earth itself. If an object is at a certain height from the earth, it will have a kinetic, it will have a gravitational potential energy, GPE in short I call it. Kinetic energy will be there when a body has a velocity and a mass. Gravitational potential energy will be there when a body has a height and a mass. That's it. Remember it this way. When a body has a mass, has velocity, that is a body which is having mass and is moving, it will have kinetic energy. On the other hand, a body which has mass and is at a certain height, it will have a gravitational potential energy.
Okay.
If you lift an object, so what you are doing, you're lifting a mass at a certain height from the earth. That means you are giving the object to have some gravitational potential energy in it. You're storing some gravitational potential. You're working for storing the gravitational potential energy in the object. Okay. What is the formula again? So this GPE, okay, let's call it U only, capital U.
Okay.
Potential energy is often represented by capital U. So capital U formula, before formula, let's find the formula together. Will it be directly proportional to mass? Yes. Heavier the object, isn't it tough to lift it up?
Yeah.
It is. So that means more the mass, more is the potential energy, because the work you are doing, that will be stored in the form of potential energy. So you must have to do higher amount of work in lifting a heavier object. Will be storing a higher amount of U, potential energy. They are directly proportional. So heavier the object, higher amount of gravitational potential energy the object will store. Lighter the object, smaller energy it will store. Right? Second thing is, will it be directly proportional to height also? Higher the object is, more amount of gravitational potential energy it will store. Lower the object is, it will be storing lesser potential energy. You can understand it this way. It is quite difficult to lift an object at a higher height. Okay, you can move your, or we are having a small rock. It is very small. Small rock means small mass, and a big rock of higher mass. Which one is easier to lift? Small one.
Yeah, the small one, yeah.
Because you have to do small work. Small work will be storing smaller energy, because work, the amount of work is only stored in the form of energy. So smaller work will be storing smaller energy. So lesser the mass, lesser is the energy stored. Higher the mass, higher the energy is stored. That was about mass. Let's talk about the height. Okay. Is it easier to throw a small ball to a certain height than to throw a ball to a kilometer of height?
So what? I don't understand.
What I'm saying is, it is difficult to throw an object to a higher height. You have to put more work. You have to put more efforts. If you want to throw an object to a, okay, if you are hitting in a cricket only, okay. So if the ball is at a certain height, it goes higher and higher. It is quite difficult to catch it, because it comes down with a greater energy, because it was at a higher height. And then there is a ball which only moves to a lower height. So it is easier to catch it because it stores smaller amount of energy. So this relation is applicable here also. They're directly proportional. Height is directly proportional to energy. If the object height is higher, it is storing higher potential energy. If the object's height is lower, it stores lower potential energy. Okay.
Okay.
Then comes the acceleration. Acceleration. What is acceleration? Do you remember that?
Acceleration.
Yeah.
It's
Acceleration.
like when
Yeah.
the object or something speeds up and it also changes direction and it changes speed as well.
Okay. So acceleration is the rate of change of velocity.
Oh, okay. So the same.
Yeah, you said it right. But it's simpler than that. The rate of change of velocity.
Yeah.
So if the object has a higher rate of change of velocity, it will be having higher potential energy. And you will combine all these three, again, you will get something. U is directly proportional to mgh. mgh. When you will remove the proportionality sign, it will be coming with a equal to sign and a constant. Fortunately, the constant value here is 1. So U equals mgh. This is your formula for potential energy, mgh. If you know the m, the mass of the object, if you know the height of the object, if you know the g value, fortunately g value is constant on the earth. Anywhere on earth, g value is constant, which is 9.8 meter per second square. It is acceleration due to gravity. Okay, in cars, acceleration is due to the engines, but it is the acceleration of the earth itself. Acceleration driven by the earth. So if you are at a certain height, your earth will be pulling you with the acceleration of this 9.8 meter per second square. That means your speed is continuously changing by this particular rate. For simpler calculation, since it is close to 10, you can also take 10 meter per second square.
Yeah.
If you want to get the feel of g, small g, you can understand it this way. If you are at a certain height and you are being dropped from a plane, the moment you are being dropped, at the time you're being dropped, your speed was 0 because you have just been dropped. 0, right? And since your acceleration due to gravity is 9.8 or let's say 10, so another second, your speed is, in 1 second, your speed becomes 10 meter per second. In another second, your speed becomes 20 meter per second. In another second, your speed becomes 30 meter per second. That means every second, your speed is increased by 10 meter per second. So 10 meter per second every second. So s will come down and this will give you 10 meter per second square. This becomes your acceleration because your speed is increased by a rate of 10 meter per second every second. Anyways, so g value remains same for this particular formula. You only have to account mass and height, you will get the potential energy. Okay, so what kind of question they may form us? They will give us the mass of an object, they will give us the height of the object. They can say there is a object of m mass kept at h height, find the potential energy. So multiply the m by gh, you will get the potential energy in the values joules. Only when your height was in meters. If it is not in meters, so convert that into meters first. Your g value will always be 10 meter per second square, you can take it. Okay.
Yeah.
And mass will be given in kgs. If it is in grams, so you have to convert that into kgs first.
Okay. I think I need a more help on that bit.
Yeah, so just remember the formula mgh. You know the values. Mass will be given, height will be given. You have to put g value. G value is 10 in all the questions. It will be the same because g remains same. It is for the earth. For every planet, g value is same. Moon has a value of g, I think 6 point something, 6.88. Moon has a lesser value of gravity. Moon has lesser gravity, you know. Your height will be increased at moon due to the lesser gravity at moons, because your spine due to the gravity will be slightly opened up. Your mass will also be lesser. Okay. There is one more thing in conservation of energy only, since we now understand kinetic energy and potential energy completely. Okay, see, these energy act together in real life. Kinetic energy and potential energy. If a car is moving, so it must have kinetic energy and potential energy at the same time. Okay. If an object is moving up, so higher it is moving, higher it moves. What is happening? If I'm throwing a ball up, so the moment I threw it, the kinetic energies was highest at this point, and as the ball is going up and up, the kinetic energy is reducing, and at a certain height, the kinetic energy will be zero. And at this point, the ball will be having all potential energy. Okay, and then again the ball will fall back on the earth. So this potential energy, which was maximum at the highest point, now will now be turning into kinetic energy again till it hits the ground. Once it hit the ground, its kinetic energy is again zero. So the swap is happening simultaneously, right? Togetherly they are called as mechanical energies, kinetic energy and potential energy. If they ask you what is mechanical energy, so kinetic energy and potential energy are togetherly known as mechanical energy. And total mechanical energy of an object is constant. Constant. What does it mean? Constant. So what is total mechanical energy? Kinetic energy plus potential energy.
Yeah.
It is mechanical energy together, and it is constant throughout the journey. It's not changing. The sum of them will be changing always at every point of the journey. What is the journey? I'm taking an example again. You are there and you throw up ball from this particular point. The ball goes higher and higher. See, the moment you threw it, the mass of the ball was m and the velocity was v, right, at the time of throwing it. So what is the kinetic energy of the ball? Kinetic energy of the ball initially was half mv square, right? As the ball go higher and higher, its velocity will be decreasing, isn't it? It will be decreasing. It is decreasing. It is keep on decreasing, right? At a certain time, when the ball reaches its maximum height, at this point, all its potential, all its kinetic energy, half mv square, is now vanished. It's gone. Gone to where? In the form of potential energy. At the maximum height, it gets stored in the form of potential energy. In the journey, when you were observing your potential and your kinetic energy is reducing, because earlier it was half mv square and your v value is continuously decreasing in the way. So your kinetic energy is also decreasing in the way. So where is the decreasing amount going on? It is getting added into potential energy. And the moment when the kinetic energy becomes zero, so all the kinetic energy is now stored in the form of potential energy. Okay. Then again, when the ball will fall back, all the potential energy will be gradually, because height is maximum at this point, height is half at this point, right? And height is zero at this point. That means your potential energy, which is equal to mgh. So it is maximum. So potential energy was maximum at the h height. At the half of the height, potential energy will be half. And as the ball hit the ground again, the height is zero. Potential energy is zero again. So where does all the potential energy is going? Because it is reducing from full to half to zero. Where is it going? It is getting turned into kinetic energy again. So the conversion is continuously happening, and at any point of observation, if you are observing here only, as the move is, as you have thrown the ball in the upward direction, so at any point when you will observe it, your sum of kinetic energy and potential energy is something. You find it, right? I'm calling it ki initial, pe initial. Kinetic energy initial, potential energy initial. And then when the ball is falling back, and at this point I'm observing now, I'm calling it final point. So the sum of kinetic energy and potential energy will be same as the initial one. So at all points their sum will be equal. I'm not saying initial kinetic energy is equal to final kinetic energy. No, I'm saying sum of these energies, kinetic and potential, at any point of the journey will always be equal in all the systems. And the principle is known as total mechanical energy of a system is constant. Okay, in higher grades, we explain so many concepts using the total mechanical energy concept. The energy remains constant at every point in the journey. Okay. So we have seen kinetic energy, we have seen potential energy, specifically gravitational potential energy. Now one more energy we are having, elastic potential energy.
Is it the last one?
Yeah. In our syllabus, we are only having three energies: kinetic, gravitational potential energy, and the elastic potential energy. So, what is this elastic? From the name itself, it is very clear. The energy is stored in the object when it is stretched, or compressed, or twisted. This energy is elastic potential energy. In short, I'll call it elastic energy. When the object is stretched, so when the object is stretched, and the moment you release it, what makes the object to regain its shape? The moment it is released. What makes the object to regain its shape? It is the elastic energy stored in it the moment you are stretching it. When you are stretching it, you are storing the energy. The moment you release it, the stored energy will now be used in regaining its shape. There is a rubber toy. I am twisting the rubber toy. So while twisting it, I am continuously storing the elastic energy in the toy. At the moment you release the toy regain its shape, the original shape. What makes the toy to regain its shape? The energy which you were storing continuously while twisting it. That is the elastic energy. So three things can make the elastic energy being stored: stretching, twisting, and compressing. Okay, we are only having one law because we always found a formula for all kinds of energy. Formula for kinetic was half mv square. Formula for potential was mgh. We need to find the formula of elastic energy also. So the person who get the credit for the elastic energy was a Hooke's law, we call it. His name was Robert Hooke, the person who discovered the cells in your biology, the same guy.
Yeah.
Okay, he appeared in all the texts, in physics, in chemistry, in biology, in architecture, in English also. Okay. He told us the elastic energy is no different. The formula of elastic energy is same. Energy equals force times displacement. That's it.
Yeah.
For example, you are having a spring and this is your wall, and spring is now connected to the ball here. It is right now in its original shape, neither stretched nor compressed, in the original shape, right? And the moment I stretch it, so this is the extended length now, the red color I am showing, that is the extended length. So you must have applied a force in stretching it, F force. And since you stretched it, so the spring is now elongated with some distance, d. When you put these two values in the formula, F times T, you will get the elastic energy. That's it. FD.
Okay.
Just remember that from where you are measuring the distance is not measured from here. No, distance is measured from the normal length. If they say the normal length of the spring is 2 meters, and the spring is the elongation of the spring is 1 meter. So you don't have to count 3 meters, 2 plus 1. No, you only have to count elongation in the spring. Your D is elongation in short. It's not the length of the spring. D is not the length of the spring. D is the elongation in the spring. Okay. This was about finding the energy, elastic energy. I also told you that this force is applied by the person who stretched the spring. Okay, but in the formula we call this force as spring force, as D has a special name, not displacement but elongation. In the same way, force has a special name, spring force. Spring force. Okay, why I'm calling it a spring force? Even though the person is applying the force. Okay, so the thing is, the spring force, the force that a person externally applied, okay, that will be equal to the spring force also, because the moment you release the spring from here, from the elongated length, the spring will regain its shape. With what force? With the force that you already applied. It's the same force. And but since the spring is applying this force this time to regaining its shape, this force is known as spring force. That's it. Okay. I'm just saying that I'm not saying it forced by a person. I'm saying it forced by the spring itself, which do not see in the first glimpse, but in the second glimpse it is clear. The moment you release it, a spring also apply a force backward to regain its shape. This force is spring force, which is exactly equal to the force that you applied already in stretching it. So mathematically they are same, but we call it spring force, Fs in short. So the formula of spring force is spring force times elongation will give you the elastic energy. Clear? Okay, why I was saying about the Hooke's law. So spring force was quite important because it was discussed in the Hooke's law only. The Hooke's law is all about the spring force. Sorry. Hooke says one thing, that if you are having the force F equals kx. This is the formula of spring force. What is it? Okay, because in the formula of spring is the elastic energy, I already told you, force times elongation. D is the elongation in the spring, not the length of the spring, but the elongation. F is the spring force, which is exactly equal to the force applied by the person. What is the force of F? The formula of F is given by the Hooke's law. Just remember it. This Hooke's law says the spring force equals to kx. Again, what is x and what is k? So this x is the elongation itself. The same thing, the d that you are taking the formula. What is x? X is the spring. What is k? K is the spring constant. It is the property of material. Once you choose your spring from the market, it has a specific value of k. It will be mentioned on the wrapper of the spring. Okay, every material has a specific value of k. Even you and I will be having a specific value of k. Okay, k is known as spring constant. The value of k will be given in the question. Elongation they will give us. For example, they will say the spring is stretched by 2 meters. So 2 meters is the elongation. A spring constant is given. When you multiply these two, you will get the force. You will get the spring force. Okay. Your k value is a materialistic property. Every object has a fixed value of k. The k value tells you how stiff is the body. How stiff is the body. So, for example, the car suspensions, they may have a k value of 50,000 Newton per meter. Okay. And a soft slinky toy may have a k value of 1 Newton per meter. What does it mean? That means in order to stretch a slinky toy by 1 meter, you only have to apply a force of 1 Newton. Easy force. But in a car suspension, if you want to move the car suspension by 1 meter, you have to apply a gigantic force of 50,000 newtons. So K value tells you how stiff is the body. Our bones are very stiff, our muscles are less stiff. So K value is higher for the bones than the muscles. Okay, so this was the formula of energy, F time displacement, which is always applicable for kinetic energy, for potential energy. And every time we discussed a dedicated formula for each of them. The formula of kinetic energy was F time displacement also, or half mv square. Formula of potential energy was mgh. Okay, this is a fundamental formula. All the formulas are coming from here only. But we need a dedicated formula, half mv square for kinetic energy, mgh for potential energy. In the same way, we need a formula for elastic energy also. And the formula of elastic energy is half kx square. Half kx square. K is the spring constant, x is the elongation. That's it. In the question, they will give you the value of k, they will give you the x value, and they will ask you the elastic energy. Okay. These were the following energies we already needed: kinetic energy, potential energy, and the elastic potential energy. Now comes the power. So power is what? Power is the rate of doing work. You are more powerful if your speed of doing work is higher. You are less powerful if your rate is the speed only. Speed of what? Speed of doing work. Speed of expending your energy. So power is the rate of doing work. The rate of doing work. Rate of spending the energy. Same thing. Energy and work are the same. What is the formula of power? The power is represented by capital P. The formula becomes power equals work done per unit time. In a unit time, how much work you can do. That is your power. Also, in a unit time, how much energy you can spend. That is also your power. The units. So the unit of energy is joules. Energy. The unit of time is second. The unit of power becomes joules per second. Joules per second is also known as watt, WATT, represented by capital W. Capital W, watt, is the unit of power, SI unit of power, which is also equals to joules per second. But rather writing joules per second, 2 letters, we have chosen a single unit, watt, which represents joules per second, represented by capital W. Okay, what will you understand with 1 watt? So 1 watt only means that a body will spend an energy of 1 joule per second. If your power is 1 watt, you are spending an energy of 1 joule every second. That is your energy. If you ever, okay, you can just take any electric appliances in your room and you will check the power rating. It will be mentioned on the back of the electric appliances. Then you will see power rating will be mentioned on it. Okay, what will it represent? For example, okay, I am having my phone adapter and the power rating of the adapter is 45 watts. So what does it mean? The power of my adapter is 45 watts. That means my adapter is consuming an energy of 45 joules every second. Okay. Certain devices like your air fryer, so it will be having a power rating of 1 kilowatt, 1000 watts. Kilowatt means 1000. So that means your air fryer will be spending an energy of 1000 joules every second. This is what we understand with the power. So it is good to have appliances with greater power rating or lesser power rating? Lesser. Why will you want your appliances to consume higher energy? Because if your appliance is consuming higher energy, you have to pay higher bills. See, my adapter is only consuming 45 watts.
That means there's more power.
Yeah, that also makes sense. 45 watts is being consumed from my electric board, but it is also given to my phone in single second. So my phone will be charging faster, right?
Oh,
So if you're having an adapter of 80 watts and an adapter of 40 watts, which one will charge your phone faster? So 80 watts one will charge your phone faster because 80 watts adapter is transferring 80 joules of energy per second in your phone. And the 41, the 40 joules, 40 watt adapter is only transferring 40 joules of energy per second to your phone. Slower, it will charge your phone. But always when you visit a electrical mart, you always check the power rating because you want appliances of lesser power rating. Sometimes you don't want things to be done faster. You want things to be done affordably, right? Okay. So we get to know the formula of power, which is equal to work done per unit time, energy over time. The unit watt is named upon the person who discovered it. It was James Watt, who discovered the first steam engine. And the unit is named upon his name, James Watt. He created a steam engine. Steam engine is used for powering the trains or industries. Okay, so this is why we named the unit of power on his name, James Watt. Earlier than that, the power was measured in horsepower, HP.
yeah.
He himself named or power rated his engines in the horsepower, because earlier days horse were doing all the power work. So 1 horsepower means energy spent by a horse, okay, in moving, let's say 100 meters in 1 hour. This was horsepower. Even today we use the unit horsepower. 1 horsepower stands for 746 watts. Okay, it is the energy 1 horse spent in moving, let's say 1 minute for 100 meters. Okay. Let's talk about the efficiency also. I told you efficiency means how efficient is the appliances. Efficiency is measured in the percentage. You want to get appliances of greater efficiency. What is efficiency? That means your device is consuming, okay, what amount, okay, efficiency percentage will be useful energy output. Useful output of energy over total input energy times 100. For example, if there is an air fryer which I am giving a total input energy of 100 joules, okay, that is total input energy. Total input I have given. Now it depends on the air fryer. If my air fryer is not efficient, is not good, what will it do? It will not use the total 100 energies at output. What is the output of air fryer? To air fry the things. So in air frying, it is using only 20 joules, and in getting heated up, in creating sounds, okay, in creating all the other things which is not useful, because the only purpose of air fryer was to air fry the food, but in doing the other wasteless things, creating sound, okay, creating heat, it is wasting 80 joules. So how will you rate the power? This is the wastage, this is the useful energy. So how will you find the efficiency of your air fryer? So efficiency percentage will be useful output. What is the useful output? Only 20 joules over total input output, which is 100 joules, times 100, 20%. So your air fryer is only 20% efficient, which is good. Okay. the LED bulb which we earlier used to use, the yellow bulbs, okay, in 90s era, these bulbs have an efficiency of 1%. If you are giving 100 joules of energy, 99% is wasted, only 1% is used. But right now we are using the LEDs and all, so they are using the energy efficiency of 15%, 17%. If they are consuming a output of 100 joules, input of 100 joules, the output useful is 15%, 85% is still wasted. But still then we say they are efficient, because as per our today's technology, we are doing well. It is considered a good growth. 15% efficiency. Okay. The best efficient devices that we see in the market, they are highly efficient. I think they can be efficient as 30%, 35%, not more than that. We are still trying to make devices more efficient.
Yeah.
But still there will be some wastage. We cannot avoid that. Okay. Now comes the last thing, which is energy resources and the real world. So where our energies come from? That's a theoretical topic. So where our energies come from? So all the energy human uses, it comes from one of the 4 places. What are these 4 places? Either it comes from the sun. Okay. 4 sources of energy on earth. Sun, or the earth's interior, the volcanic eruption and all, right?
Yeah.
Guess the third one. What is the third? What can be the third source of energy? Sun, earth's interior, and
Light.
light is coming from the sun only. It is the tides, oceanic tides. Okay. And the fourth way, the last way of energy that we are having is a nuclear process, which we harness from whatever we are already having on the earth. Nuclear process. These 4 sources of energy we are having naturally. Every fuel we are burning, every renewable energy we are harnessing, it is coming from one of these 4. All the renewable energy that we are having, they are a consequence of these 4. Okay. Since I'm using the term renewable energy and non-renewable energy, how will you define renewable energy? So renewable energy is the energy source, or a renewable resource is the energy source which is continuously renewed. Okay. It will never get exhausted on earth. Like fresh water. Fresh water is a renewable resource. Okay. Wind power is also a renewable resource. On the other hand, fuels, fossil fuels, they are non-renewable resource, and we are at the brink of exhausting them completely. I think by the year 2052, we will be completely gone with the fossil fuels. This is why we are continuously trying to make our energy resources completely based on the electrical appliances or the hydrogen powered vehicles. And this is a big concern for the Middle East countries, because once the oil is gone, they have nowhere to go. This is why they are switching their economy for tourism more now. Also, okay, so now we understand renewable and non-renewable resource. Which get renewed over time, it is renewable. Which do not get renewed over time, which get exhausted, is non-renewable resource, which is existing in a finite supply.
Yeah.
Okay, for Australia's case, so historically they are dependent over the coal for electricity, but the changes are happening very fast again, because coal is a non-renewable resource, so we have to switch to the renewable resource. In India, people are switching for the solar. The government is planning or like a normal household also in India, on an average, they are having a solar power backup for their energy supplies. They won't require any government aid or any power plants because they are being self-sufficient by using the solar plants and all. Okay.
Yeah.
Although solar in particular is booming in Australia also, since it lies at a prominent location. Australia has the highest average solar radiation per square meter of any continent.
Yeah.
But in your country, coal still supplies the largest share of the grid's electricity. Your electricity is still coming from the coal. And what is the next growing resource in there? So it's solar. Your government is trying hard to make it solar this time. Also, in southern states like Victoria, they are trying to make it through wind also. It's a major contributor now. Hydro,
Yeah.
okay. They are also trying to make it through hydro ways. They are creating storages and backups. Now, battery storage is also rapidly expanding to handle the latency that may come due to the solar and wind. So, like Australia, all the countries are now switching their ways for the renewable sources of energy. As you have seen, like as the war of Iran and America, people were very dependent over the fuels, fossil fuels. So more countries are now trying to be independent, at least on the fuel sides. That's all for today. Okay, and here we ended the energy chapter. We are meeting on Thursday.